Hi everyone, my name is Alexander Beischel and I will present our paper Profiling Dataflow Systems on Multiple Abstraction Levels. This was joint work with Timo Kersten, Maximilian Bandle, Jana Gitscheva and Thomas Neumann. And in our paper we show how to profile compiling dataflow systems at multiple higher abstraction levels so that all developers of the compiling dataflow system can benefit from comprehensible profiling results that actually match the components of the system they are working on. Then, with these comprehensible profiling results, they can make well-informed decisions to carefully tune our system. Compiling dataflow systems are very versatile and used in multiple areas, from machine and deep learning frameworks like TensorFlow, over graph and stream processing, and even big data processing, for example with Spark. But they are even used in more traditional categories, like for example database management systems, with the compiling database management systems on the rise. The compiling dataflow systems help us to address the increasing heterogeneity of available hardware resources by generating code for the system's underlying hardware. In addition, they divide the complexity of generating optimized efficient code over the entire system stack by applying multiple expressive abstraction levels. However, probably every one of you working on a compiling dataflow system has already experienced the following situation. So, I'm running a dataflow expression in a domain-specific language or a query in my dataflow system. Now the system takes my expression or query, parses it, optimizes it, and then generates query-specific, highly optimized code that is optimized even for my underlying hardware with its code generation engine. Then I compile the generated code and execute it to actually process my query. However, for some unknown reason, my query execution time is slower than I had expected. As a good engineer, I now want to figure out why it took more time, so why we were slower. So I want to locate the bottleneck and then carefully tune it to make my query super fast again. In order to do that, I now execute my query again, but this time I profile the execution of the generated code using a profiling tool, like for example vtune or perf. So now perf will hopefully tell me exactly where my time was spent, so I know which part of my dataflow system I have to improve to make my query super fast again. So let's see what's the root of our delay of the query execution. But these are actually the results I get. So now I see that this particular line of assembly code is quite expensive. But it doesn't match any of the code I wrote in my dataflow system, and I can't even attribute it to a certain part of my query. So in short, I'm no step further and I will have to spend hours of reverse engineering to figure out to which part of my system this line belonged and what's the root of my slower query execution time. But the question is, why can't we just map our profiling results back to the components of my dataflow system like we do it for not code generating systems all the time? The reason is the following. Compiling dataflow systems take our query, transfer it to a dataflow graph, and then they perform multiple consecutive lowering steps to perform complex optimizations like operator fusion or reorderings. In the last lowering step, our dataflow system's code generation engine generates query-specific fast code optimized for the underlying hardware. Then we execute this generated code by first compiling it and then executing it to actually run and process our query. Now, if we profile the query execution, we don't actually profile our dataflow system itself, but the generated code. Now, due to assigned debug information, we can map the instruction pointers contained in the profiling samples back to machine IR or assembly instructions of our generated code. But still, the profiling results we get are for our generated code and not for the components of our dataflow system itself. Now, these results might be useful for the developer of the code generation engine, because he's familiar with generating code and can optimize part of the code gen engine itself. However, those results are far too low level for any higher level developer because they just cannot map the results to the components they're actually working on. But still, they need profiling results that match the components in the higher levels of our data flow system to optimize our entire data flow system itself. So usually what we can do in traditional systems that don't generate code, if we cannot map the source line we get in our profiling sample to the components of our system, we use call stack sampling, for example. Then, if we have a sample for which we don't know where the source line actually belongs to, we just inspect the also recorded call stack to match it to the component we actually need. Now, unfortunately, this won't work for compiling data flow systems. The reason, therefore, is the following. Compiling data flow systems first lower our query and generate code to execute the query. Then we execute this generated code. Therefore, we decouple the code we actually generate and execute for our query from the internal components of our data flow system, because we generate the code and then we compile and execute it. Therefore, the query execution code is decoupled from the data flow system itself. And with this, we lose the connection between the internal components of our system and the actually executed code. So call stack sampling won't help us anymore as well. But we still need to re-establish the connection between the generated code we actually execute in our data flow system's internal components to optimize our system again. Now, if we are able to re-establish this connection and close the gap, we will also get comprehensible profiling results again. Now, we did this with tailored profiling, inspired by the way debuggers attach debug information to map the instruction pointers back from the samples we get with instruction pointers to machine or assembly instructions. We developed tailored profiling, and what we do is we re-establish the connection between the generated code and the data flow system's components by tracking the connection between the components of our system over all different abstraction levels from the data flow graph down to generated instructions during the lowering process, and then we preserve this information. Now, after profiling our query execution, we can take this information and map the samples which contain the generated instructions in a bottom-up fashion back to the components of our data flow system. Doing this, we then get comprehensible profiling results again because we can attribute the generated instructions for query execution to the internal components of our data flow system. And we do this by using two main ingredients, the tagging dictionary and register tagging. So what we do first is, during the lowering process, we already have all information available we basically need to connect the components of the different levels up from the data flow graph down to the generated instructions that our code generation engine actually produces. But what we do usually is we just drop this information. Now, with tailored profiling, we preserve this connection information and store them in a central tagging dictionary. Then, for each of our samples, we can just look up the entries in our tagging dictionary to map the generated instructions in a bottom-up fashion to the components of the higher abstraction levels of our data flow system. Now, after we've connected all samples of the executed code to the components of our data flow system, we have comprehensible profiling results again, and the developers just need to aggregate the samples on any level they need for more insights of their component in the data flow system. So now you saw how the tagging dictionary works conceptually. Let's have a look at a short example to show you how it actually works. So for simplicity of this example, we will directly lower the data flow graph immediately to generated code, and we will skip all intermediate steps of the lowering process, but we explain them in far more detail in the paper, also with some examples to show you how to track the connection over multiple abstraction levels. Now, for this example, when we generate code, for example, for our scan operator of the data flow graph, we store a mapping entry for each generated instruction we have. This generated instruction maps to the actual operator of the Dataflow graph for which we generated this instruction. So what we can do then is, if we have a sample that contains a generated instruction, we just look it up in the tagging dictionary and see to which of our operators our entry belongs. You can just imagine it like a hash table where I insert my keys with values, with the instructions being the keys and the values being the Dataflow operators. We do this for each of our operators, and basically we just add a mapping for each of the generated instructions in our generated query code program. So by doing this, we can map all of our instructions to the operators of the Dataflow graph. However, there's one small exception. During the code generation, we sometimes just generate code for a shared function once, for example for malloc, and then from within our generated code, we'll call our shared function malloc from multiple different locations in the generated code. So for example, our scan operator will use the function malloc as well as our filter operator. Now, if we get a profiling sample that contains executed instructions from within our shared function malloc, we cannot uniquely identify which operator actually called our shared function malloc and executed those instructions. So to which of our operators the instructions belong. Could be either scan or filter operator. One way to solve this is using call stack sampling. Again, we record the entire call stack in each sample. If we have a sample of a shared function, we inspect the entire recorded call stack of our generated code to see which of the operators called the shared function. However, call stack sampling is quite expensive, sometimes multiple times of the actual query execution. Now, since most compiling Dataflow systems run on native hardware and have full control over the system, we came up with a far more lightweight alternative, which we call register tagging. Just for comparison, register tagging has a query runtime overhead of 3%, while call stack sampling can take multiple times of our actual query execution. And register tagging works as follows. At first, we tell the compiler to exclusively reserve one machine register for our register tagging method. Therefore, this machine register will be excluded for the Dataflow system, but only our register tagging can use it. Now we will use this machine register to track which operator actually called our shared functions. Therefore, we enclose each call to a shared function by tagging instructions that write a unique tag in this machine register before calling the shared function. And then when we execute the code of the shared function and take a sample, in addition to the instruction pointer, we also record the content of this machine register. And as this machine register contains a unique identification tag, if we have such a sample of a shared location, and we see in the tagging dictionary we have multiple potential operators, all we need to do is have a look into the also recorded tag of this machine register. Then we know exactly who called it. The nice thing is that most profiling tools already support recording contents of machine registers, so therefore we don't need to change the profiling tools itself. Now, after we called the shared function malloc and return, we just unset the tag again, so we reset our machine register, and we do this for each call to a shared function of each of the operators. And with this, we can now disambiguate also calls of shared functions. So now we can uniquely identify for each of our generated instruction to which component of the Dataflow system it belongs by using the tagging dictionary and register tagging. So now you saw all the components you need to actually apply tailored profiling. In addition, register tagging can also handle multiple abstraction levels with shared functions, and we explain in the paper how this works and compare it even more to call stack sampling. But now that you've seen how it works, let's have a look at what it can do for you. So we've implemented tailored profiling in our production-ready compiling Dataflow system Umbra, which is a relational database system. And all the cases I will show you now are real-world results we got after integrating tailored profiling. So what we can do now with tailored profiling is, when executing a query, we can directly attribute the time of our query execution we spent in each operator of our Dataflow graph. But we cannot even not only do that, but we can also track the activity of each operator over the entire query execution time to see how the different operators interact, how they have correlations, and we can also detect local bottlenecks to tune them even faster. Tailored profiling is also not limited to just tracking like activity of operators, but it can, independently of the performance event, map the samples back to our components. So we can use basically all of the available profiling events to get more information insights for our system. For example, like memory access patterns when we profile memory loads. So now you saw what we can do, but how much effort is using tailored profiling. So implementing tailored profiling in our system was quite little effort. Umbra has approximately 22,000 lines of code for the code generation engine, but we just needed to add 56 lines of code to integrate the tagging dictionary, register tagging, and tracking different components over the different levels. So you see, we just had to add very little amount of codes, lines of code to integrate tailored profiling in the code gen engine. Then, in addition, we just added around 1,600 lines of code in a new component of our system, which basically just does the sample processing after executing the query and creating the visualizations you just saw. So the implementation overhead is quite small. Also, we already achieve a very high accuracy of 98%. So we can basically map 98% of all samples to the components of our system. The remaining 2% are either samples without valid instruction pointer or are attributed to libraries where we haven't added support for tailored profiling yet. And how high is the overhead compared to call stack sampling and existing methods? So tailored profiling has very little overhead during query execution time to not distribute the query execution itself. The tagging dictionary is populated at compile time, so before we generate our code to execute the query itself. Therefore, it doesn't inflict with our query execution itself. Register tagging, so exclusively reserving a machine register and then writing our tagging instructions, took on average over all 22 TPCH benchmark queries 3% performance overhead. In the figure on the right, you can see the comparison between call stack sampling in red and then in green, normal PMU sampling, and in blue, tailored profiling combined with normal profiling, so taking the samples. As you can see, the blue and the green line are nearly identical because the only overhead we have, in addition to the normal PMU profiling, is register tagging with 3%. In difference, you can see how soon call stack sampling increases in terms of costs when we increase the accuracy of taking the samples. So if the frequency of taking samples increases. So we are much cheaper than call stack sampling. And all of this, just to recap, is now possible because tailored profiling closes the gap between the Dataflow system and the generated code we actually execute. Thereby, we can map the samples of our executed code back to our system's components and provide results useful for all developers. Our approach is very lightweight and can map nearly all of our samples back to the components. Also, as the implementation effort is quite slow, tailored profiling can be transferred to many systems. And our current implementation prototype in Umbra already supports profiling the code executed at the CPUs of multi-socket and multi-core machines. Future work now is extending tailored profiling to heterogeneous compute resources in distributed systems. The main challenge here is not the concept of tailored profiling, but combining the profiling results of the different hardware units. But this was just the tip of the iceberg. The paper contains more technical and implementation details. For example, we show how to use the tagging dictionary for multiple abstraction levels, and we discuss register tagging and call stack sampling and compare them in more detail. Additionally, we show, for example, how to use register tagging if we have shared functions and shared sys locations on multiple different abstraction levels. Also, we discuss which optimizations are actually supported by tailored profiling. We dedicate, in addition, an entire chapter to the integration of tailored profiling into our compiling database management system Umbra. And our evaluation contains more details, for example, in terms of runtime overhead, also memory footprint, and we have 3 very detailed use cases that show you the potential of tailored profiling. And all of those use cases were things we actually already did with tailored profiling. So thank you very much for watching my talk. Stay healthy, and I'm looking forward to seeing you at the EuroSys conference.